Okay, welcome back, everyone. Thank you. Our last session for today will be on DC system monitoring. This is something that we've taken for granted in the Dranetz products, I think, dating back to the 1990s, mid-1990s. Every three-phase portable, in fact, most of our fixed products have had the ability to measure DC at the same time as you can do AC. So you can measure both AC and DC on your primary channels, where some applications have AC on the primary channels, and I mean channels A, channel B, channel C, and then measure DC on the neutral channel. A lot of applications have that. So we've had DC capabilities, and it's a time that we actually described how to set up the instrument. So the HDPQ Plus and SP have the capability to measure up to 1,000 volts AC or DC. Just a note on the SP, one of the differences and advantages to the SP models is that it has the ability to power from the phase being measured. The little connectors around the side of the instrument, you would jumper your usually phase A voltage around to the side of the instrument to power the instrument. However, it's important to note that that power supply, that separate power supply is limited to 600 volts AC and 500 volts DC. So if you're measuring above, again, these limits, you need to derive the power from the instrument from just a 120, 230 volt wall outlet or something within this 500 volts DC and 600 volts AC limit. Okay, so just a note. But the DC monitoring that we're going to talk about is exactly the same, whether you're using a Plus or an SP. And it's the same for each model, Visa, Guide, Explorer, and Explorer 400. Okay, so there's nothing unique about the two instrument mainframes or the models that we're going to talk about. The important thing is DC monitoring is very much the same as AC monitoring. There's only one thing you need to do. And the DC monitoring applications, well, there's a lot of applications, but the most common ones are UPS battery strings. You'd be surprised how our instruments are used both on a portable basis, but also on fixed systems to monitor UPS battery strings. And a lot of our fixed applications will have the output being monitored on AC and the DC string being monitored using the neutral channel or the D channel of the instrument. And very similar to solar inverters and solar strings can be used for DC, but also DC power distribution. There's a whole sub-industry for DC power distribution. Again, the only thing you need to make sure is that it's under 1,000 volts for the HDPQ family. That's 600 volts for our PX5 family, which predates this, but make sure you're within the ratings of the instrument is the key. So what are the considerations? There's one and possibly two considerations. The first one is the voltage connections are direct up to 1,000 volts. Nothing you need to do, okay? You may need a divider if it's above that, but it's a direct connection to the instrument. Just be sure to use our PR150 or our PR1500 CTs. The regular Flex CTs and our TR clamps like our TR2500 and 2510, they cannot sync or measure DC. Only our PR family of CTs can do that. Now, how do you set up the instrument? We're on that same screen that Thurman showed you before, but we're choosing internal sync, which means that the instrument is not trying to synchronize to a 50 or 60 hertz AC waveform. So we turn that off. In fact, if you even skip this step, if the instrument won't be able to sync to DC, it'll probably just default to the internal. But to make sure
that's correct, Ross.
All right, thank you, Therm. But just to make sure, then it'll be locked onto internal sync, so you don't have to worry about that. Other than that, there's absolutely nothing that you need to do. All of the voltage trending, the current, the power, everything but harmonics, because there's no harmonic measurements anymore. Everything will ripple through the system normally. And you would use the same peak transient settings. The wave shape transients will work just the same. The only transients that we don't recommend that you do is the high speed transients for the Explorer. They're kind of tuned around the AC measurements, but otherwise you're not going to get anything different out of the instrument or as far as its capabilities other than what I just mentioned before. So Ken Thurman, do you have anything to add to that? I think we covered it.
No, I think it's really that straightforward.
Yeah,
What you
that's
see
not too
there
much.
is what you get, and you're setting your trigger limits. Especially for RMS, which is usually the most common usage of monitoring DC, is to know when you go above or below a certain trigger point. They're the same as if it was an AC application.
Yes. Okay. Thank you. Thank you. And that's it. I mean, we oversimplify it a little bit because it is very simple and it's taken for granted on the Dranetz products and certainly on the HDPQ family. So, okay. I don't see any chats regarding the DC current. So we're going to wrap it up. Thurman, Ken, and I will remain here to take your additional questions via chat.
There is, I'm sorry, Ross, there is one
Okay. I
question.
missed it. Go ahead.
This is from Michael. I'll take this one. The question is, what does the HDPQ provide which you can't get from a VFD? Well, Michael, there's a couple different approaches. It all depends on what the objective as far as monitoring the VFD. It can range from monitoring the input to the VFD to simply see if the VFD is exhibiting the harmonic pattern that is expected. And if you have a VFD that might be failing or might be misoperating, usually that's one of the first approach. If it's your typical what we call 6-pole converter, which your dominant harmonics are going to 5th, 7th, 11th, and 13th, then you monitor the input to the VFD to make sure that those harmonics are what they're supposed to be. And then as far as monitoring the output of the VFD, if you have, let's say you have premature motor failures that are connected to a VFD, well, then, you want to troubleshoot that. And, what I mentioned earlier, the most common that we see is the magnification of transients from the VFD, pulse width modulated waveform output of the VFD that magnifies when it reaches the motor terminal. So it really depends on, at the end of the day, what the approach is. To Ross's point, it might be something as straightforward as, okay, I want to, trend the power, the kW output of the VFD, voltage and current, and even frequency to some respects. So there's numerous different approaches that you can apply to this that the VFD is simply not going to give you.